Okay, so we're gonna get ready to start now. We're gonna go now to the next unit, which is unit 8. We're gonna talk essentially, we're gonna develop the quantum model of electrons a lot deeper. We're not gonna go into the math of it, okay? Don't worry about it. But I'm gonna try to give it some sense. Now, the majority of you should have studied all about, you remember, right? Like, S and P and D orbitals and that kind of stuff, and electron configurations in your Chem 2 class. So what I want to do is I want to bring us back there, but kind of show you where those orbital numbers came from and what they mean, so we can expand a little bit of the application of them, all right? So let's go to our PowerPoint here. Again, like I said, this is a new PowerPoint here. This is chapter 8 or unit 8. And remember that we started out by saying, second, where are we here? I'll find my highlighter here. There you go. All right. We're going to talk about orbitals and quantum numbers. So remember, this is the model we have. We're proposing that the electron behaves as a standing or stationary wave, oscillating or vibrating between certain boundaries. Now, in this model that we had here, we developed a linear type of equation for it. But what it shows us is something interesting. Remember that if this were a particle oscillating back and forth between the two boundaries, the probability of finding that particle is the same at any point in between those boundaries, right? But notice that with a wave, what happens is that you have some areas. Let's look, for example, at the first harmonic here, n equals 1. Notice that according to this, the majority of the density of the electron's charge / mass is kind of right in between, right in the middle between the two boundaries, but it's 0 at the ends. Now, in the case of the n equals 2 harmonic, you can see where there are two places in the graph where you have a high density, a high probability of that wave being located, but there are 3 nodes, in other words, 3 areas where there's 0 amplitude. What I'm saying is that the probability in this case is going to be proportional to the square of the amplitude, because we don't want it to go with negative versus positive amplitude, right? So we're going to just take the square of the amplitude. And remember that at these points called nodes, right, where there is 0 amplitude, that means there's 0 probability. Okay, I want you to think about what we're saying. We are saying that if an electron has wave properties corresponding, let's say, to the second harmonic here, n equals 2, what that tells me is that that electron has a high probability of being in 2 regions of space without ever being in the middle. Imagine that. In total violation of classical physics. In other words, it's not like the electron is traveling from one side to the other. It's more like the electron appears and disappears from one side while it appears and disappears on the other side. It's a very interesting phenomenon that is seen in quantum physics, sometimes called tunneling. Remember that we derived this equation where we saw that the energy is quantized and is going to depend on the number n, the value of n, and also on the distance between the boundaries, which in a circular model of Bohr, it represented essentially the circumference of that orbit. But as we said, according to the Heisenberg uncertainty principle, you can't really pin down the electron into a specific orbital path. But there's another thing that we had to take into account. We had to take into account that the electron is not traveling in an orbit, which would mean that all of the points along that orbit lie on the same plane. No, the oscillation of the electron wave would happen in 3-dimensional space. So whereas, for example, in this model here that we have, a linear model, we have a single variable that we're concerned about, which is the value of n. In a 3-dimensional model, we have 3 dimensions to deal with. So you would expect that there would be like 3 different sets of variables you had to deal with. Well, this is where the Schrodinger wave equation comes in. So in 1926, Erwin Schrodinger derived an equation that was able to describe both the particle and wave nature of the electron. So what he did was he analyzed, and if you ever take a physical chemistry course later on, upper level course, you will actually derive this equation. So the wave function of Schrodinger, we give it the symbol, the Greek symbol. Why not use another Greek letter? And this is the Greek letter psi, psi. Not the guy who recorded that Gangnam Style song. No, this is psi, the Greek letter. And there's two things that are important about this wave function. It's going to allow us to calculate the energy of an electron and also the probability of finding it in a volume in space. Notice that we don't even attempt to describe a position in space, more like a volume, a region in three-dimensional space, all right? Now, it turns out that when you look at this equation, there's only one atom for which you can solve it exactly, and that's for the hydrogen atom. In other words, an atom that has a single electron, where you don't have to take into account interactions of one electron with another one. For every other atom that has more than one electron, the best you can do is arrive at an approximate solution of this type of an equation, all right? And again, I'm kind of like giving you these things here without actually going through the equations themselves. But trust me, it is a difficult approach, but it is something that, in an upper level physical chemistry course, you can do it, all right? Okay, so what we're going to find is that because we are working in three dimensions, we're going to find that there are three actual parameters that are important to the value of a wave function. So we're going to express the wave function as psi as a function of three parameters, n, l, and m sub l. The wave function is going to have the term that it's an orbital. We're going to call it an orbital. It's a little unfortunate because it sounds like orbit, and again, it reinforces this concept that the electron is orbiting the nucleus, but it's not that way. However, orbital is the name of the wave function that will have particular values of n, l, and m sub l. And these three are called the quantum numbers. Quantum numbers. All right. So n is called the principal quantum number. And just like in the Bohr atom, it has very limited values, 1, 2, 3, 4. In other words, it is a positive whole number. It is not zero, and it is not negative. Now, how can we think of this number? Well, let's see. Let's say, for the sake of illustration, that what we're interested in is what is the relative ability of an electron to have that positive attraction, attraction to the positive charges in the nucleus. Remember we said that the more you favor that kind of an interaction, the more stable you are, the lower in potential energy you are. So essentially, an electron that is close to the nucleus would be expected to have a much stronger interaction with the nucleus and therefore a lower energy, versus an electron that's farther away from the nucleus and therefore does not have that opportunity, is less stable, and therefore higher in energy. So essentially, although we cannot pinpoint the location of the electron, we can pretty much kind of map out more or less how far from the nucleus that electron is likely to be. In other words, it's just a function of probability. It doesn't really depend on, where exactly it is, just basically how far it is from the nucleus. And therefore, the principal quantum number gives us information about the distance of the electron to the nucleus, all right? And what we say is that anytime that you have an orbital, in other words, a wave function that has the same value of n, we say that these orbitals are in the same level or shell, because they're going to be very directly connected to the energy. And so we like the word level or shell because it connects distance to the nucleus with actual energy. All right? All right. Here's the second quantum number, L. This is called the angular momentum quantum number. And just like n has some limited values, so does L. L can be 0, 1, 2, 3, any number up to n minus 1. In other words, the value of L is limited by the value of n. The value of L is also a whole number, but it can be 0. It cannot be a negative number, all right? So let's play with this formula here, for example. So if n equals 1, that means that L can be 0, and then n minus 1 is 0. So L can only have one value when n equals 1. If n equals 2, then that means that L could be 0, or it could be 1. In other words, 1 less than n. If n equals 3, L could be 0, it could be 1, or it could be 2. So you can start seeing how many of these wave functions essentially are kind of like little variations of a common theme, right? So you have different combinations. So the value of L is going to depend on what the value of n is, right? um, I guess one question we would like to ask is, what does this mean? Well, let's imagine this. Let's imagine that. Before we do that, let's simplify this. Because we don't like to talk about something having a number n3 L equal 1. What we do is we've given these little abbreviations, all right? Little abbreviations. So based on the results we get from a technique called spectroscopy and the types of patterns that are generated by these different sets of orbitals, we say that when L equals 0, we say the electron is in an s orbital. When L equals 1, we say it's in a p orbital. When L equals 3, it's in a d orbital. And of course, we can go one more. For L equals 3, it's an f orbital. In your introductory chemistry class, you were taught about, s and p and d and f orbitals and all that kind of stuff. But here's where you find out where it comes from. Essentially, an s orbital is a wave function that has a particular value of n and then a value of L equals to 0. A p orbital is a wave function, an orbital, where the value of L equals 1. Notice that that can only happen if n equals 2 or higher. Because for n equals 1, L cannot be equal to 1. There cannot be a p orbital in the n equals 1 shell or level. Oh, I was going to say, where does this come from? Well, let's imagine for a moment, okay? Just imagine that the electron is like a spinning charge, right? So if the electron were a spinning charge around the nucleus, what we would say is that circular motion generates what is called an angular momentum. And in the world of physics, knowing the circumference there, or the radius actually, and the mass and the speed, you can calculate what the angular momentum is for this particle. Now, number one, the electron is not orbiting the nucleus, right? Number two, in a motion like this one, essentially the angular momentum can have a whole range of different values depending on how fast I'm spinning that little piece of metal or whatever it is that the guy is spinning here, right? But in the case of the electron, what you can see is that that's not the case. The values of this angular momentum are quantized. There are only discrete possible values of this so-called, angular momentum. Now, because that angular momentum describes a bit of a trajectory or region in space, what it is that the value of L describes the shape of the volume of space the electron occupies, all right? And again, when you have n equals 1 and L equals 0, any orbital that has the same value of L is said to be in the same sub-level. So for example, in this case, you would have level 1, which is n equals 1, sub-level 0, which is an s orbital. So we would call this the 1s subshell. Now, if n equals 2, then that is still an s orbital, but it is now in the 2s subshell. Remember, L equals 0 is an s orbital. L equals 1 is a p orbital. So for n equals 2, you can also have a second value of L, which is 1, and that's the p orbital. But in this case, it would be in the 2p subshell. Again, for n equals 3, L equals 2, what would that be? Right, it would be n equals 3, and L equals 2, we said, is a d orbital, so this would be the 3d subshell, right? Exactly. Okay, so now we're getting to build our little catalog, our little menu of symbols here. So now we know that electrons live in these orbitals that describe pretty much how far from the nucleus the electron is, and more or less what is the shape of the region where the electron is kind of like floating around or kind of oscillating around. And we have these subshells, 1s, 2s, 2p, 3s, 3p, 3d, etc., etc. Now let's look at the third number, m sub L, but I usually pronounce it ml because it's easier. This is called the magnetic quantum number. Again, remember, if you look at that previous picture that I showed you of the guy kind of spinning that piece of metal on a string. Now, he was doing it on a single plane, but remember that in real life, the electrons would be spinning, if they were spinning at all, they would be spinning all over three-dimensional space, which means that this is a moving electrical charge. And in physics, we know that a moving electrical charge generates a magnetic field. But now this magnetic field is being generated all over three-dimensional space. So what we're going to say is this number is going to have to give us a little bit of information about, okay, which way is that oscillation of the electron, which way is it oriented? Now, the value of ml now is limited by the value of L. So for a given value of L, this is the range of values that ml can have. It can go from minus L through 0 all the way to plus L, right? Notice these are all whole numbers, but notice that ml can have negative values, all right? So for example, if L equals 1, which is a p orbital or a p subshell, we would say that ml could be minus 1, 0, or 1. In other words, there are 3 possible p orbitals in this subshell. If L equals 2, then ml can be negative 2, negative 1, 0, 1, or 2. In other words, they can be up to 5 different orbitals in this d subshell, right? And what the value of ml gives us is essentially the orientation of the orbital in space. The orientation of the orbital in space, right? So essentially, there you have it. You have a function that covers 3 aspects of the wave that describes an electron. This wave is oscillating in 3-dimensional space somewhere around the nucleus. Those oscillations are quantized. In other words, they have only discrete values. And these discrete values depend on 3 parameters. How far the electron is from the nucleus, all right? What is the region of space that it is most likely in? And what is the orientation of that region in space? And this is how you describe an electron, all right? Now, it turns out that scientists found another quantum number when they started studying things. So in this experiment called the Stern-Gerlach experiment, scientists took a stream of silver atoms and passed them through a magnetic field. It is known that the silver atom has an imbalance in its electrons' magnetic properties. So the idea is that if you run it through a magnetic field, the magnetic field is going to affect and essentially detour those atoms depending on what is the value of their magnetic field. So what you would have expected was what is here on the left side here. This is the classical prediction. You would have found a smear because the atoms in this sample of silver would all have had different magnetic fields according to classical physics description of a moving charged particle. But what they found instead was that you only saw two spots. In other words, this magnetic property, whatever it was also quantized. It only had two values. And so what they did was they added a new quantum number called the spin quantum number, M sub s or ms. And they assigned two values to it. They added it to the wave function, and they assigned it values of +1/2 or -1/2. Now understand, this is a property that exists. This is a property that atoms have. It's a property that electrons are going to have. But there is really no physical explanation for it. The best that they could come up with was to say, well, if ML, the magnetic quantum number, describes the magnetic field generated by some kind of oscillation of the electron out there in space, maybe this one is generated by the spinning of the electron. In other words, the rotation of the electron. So if the electron is a sphere, it can spin either clockwise or counterclockwise, and depending on which way it spins, it can generate one or the other magnetic fields. So we can speak of, spin up as +1/2 and spin down as -1/2. For example, we can say that. I know it's very esoteric, and there is no way to prove that this spin number is due to specifically and literally the spinning of the electrons, but it's an analogy that we can use. All right, so basically now we have this wave function that describes 4 parameters of an electron: how far it's from the nucleus, what is the region of space where it's most likely to be, which way is that region oriented with respect to the nucleus, and then sort of which way is the electron spinning, something like that, this spin number here, all right? So that's what the Schrodinger wave equation comes down to, right? And the idea is that each electron is defined by a unique wave function. What does that mean? It means that every electron has a different set of all 4 of these numbers. No 2 electrons have the same exact 4 numbers. This is called the Pauli exclusion principle in honor of Wolfgang Pauli, who was an Austrian scientist. And essentially, it's kind of like, I don't know how to describe, perhaps like the way if you go to a stadium and you get a ticket, right? And it assigns essentially a seat, right, to you. So your ticket has, let's say, a section, a row, and a specific seat in there, for example. It's kind of very specific, and each seat can only hold one individual at a time, or, technically it's supposed to be that way. So the idea here is that this is what the exclusion principle says, is that every electron is going to have a specific set of 4 quantum numbers. Now, because the value of ML depends on L, and because the value of L depends on N, then there are limitations to this. And I had an exercise here, I think, where I was going to have you guys practice this. We're kind of running out of time here, so let me see if it's in there. You know what, guys? This is not in your set. Let me have you guys look at these here. All right. You may have to write it down. So here are 4 sets of numbers. Again, the parentheses enclose the 4 numbers. So they're in sequence. The first number is N, the second one is L, the next one is ML, the next one is MS. So which of these would not be allowed? All right, remember, once I have the value of N, which has to be bigger than 0, and it has to be a whole number, L cannot be negative, and L cannot be the same as N. It has to be no more than 1 less than the value of N. So let's look at the first one here. I have 3, 3, plus 1, and minus 1/2. So what's wrong with that one? Right. If n equals 3, then L cannot be the same value. So that is not allowed. All right. Remember, we said that L can only be 0, 1, 2, up to 1 less than the value of n. So the highest value you can have is 2. So the next one, it has 3. Then L equals 2. That's allowed. And the next one, ML is minus 3. But we said that the value of ML is conditional to value of L. It can go from minus L through 0 all the way to plus L. And basically what it says here, if L equals 2, then ML cannot be negative 3. It can only be minus 2, minus 1, 0, 1, and 2. Now let's look at the last one. Does that one work? Looks like it does, right? Because if n equals 2, then L can be 1. Yes, can be 1 less than that. And then ML can be minus 1, 0, or 1. So that's okay. And of course, the spin number is always either plus 1/2 or minus 1/2, right? Okay, so hopefully that's a little practice there. So again, in this case, L cannot be same as N. In this case, the absolute value of M cannot be greater than the absolute value of L. So we made that. So the third one is the only one that would be allowed here. Right? Okay, let's look at this one. I'm going to give you two sets of quantum numbers, and let's see which of those would describe an electron in a 2p subshell. Okay, here they are. So remember, 2p subshell means that n, oops, sorry. Let me do that again. So n has to be equal to 2. And for a p subshell, L has to be what? L for S subshell, L equals 0. For a p subshell, L equals 1. So which of these works then? Yep, that would work. P subshell means L equals 1. So the first one would have been something in a S subshell, except that technically there's no such thing as negative 0, but that's kind of like a little gimme there, just in case, right? Okay, so that doesn't work. All right, so we're out of time. We have not been able to finish this unit yet. And what's coming up next is actually your exam. And so, like I said, the study guide has been posted to Canvas in a separate module. Please download it because I think I'm going to have to move it from where it's at right now. Don't forget, for the exam, you'll see this in the study guide. It's all online in Canvas, but you have to take it on the assigned day and times, unless you have cleared with me that because of some extraneous circumstances, you need to scale it for some other time. Hey, I'll work with you. Okay, don't worry about it. Just make sure that your reasons are legit. Okay, don't just try to squeak by. Okay, it's not going to help if the reason is trying to I want to get more time to study. If that's the reason, it's not going to work. It's not going to help you. Trust me, it's not going to help you. You have the next few days to focus on studying for the test. And let me tell you, that experiment you're doing, that Graham's law, what did I say? Graham's law. Sorry, Hess's law. I'm sorry, Hess's law lab is going to go a long ways towards helping you study because it covers, calorimetry, Q, delta H, Hess's law, all this kind of good stuff. So it's a great exercise. That's why I scheduled it this time and structured it the way it is. Just make sure that you take your time to do it because it involves several steps, okay? So remember that the exam covers units 4, 5, and 6. So that's chemical reactions and stoichiometry, and precipitation reactions, redox reactions, all that kind of stuff. It also includes gases, applying the gas laws, doing stoichiometry with gases, using the kinetic molecular theory to explain the behavior of gases. And then it includes thermochemistry, all right? So that's what we got. So the stuff that we studied Monday and today is not included in this test. So what I'm going to do is the remainder of this topic, I'm going to record it. And I'm going to let you guys watch it on a video. So I'll do that over the weekend. I'm not going to rush because I want you guys to focus on preparing for the test. Let's see. Alexa is going to have a SI session in a few minutes when we break up here. That is a specific different type of meeting, so you'll have to log into that one with her. And please stay on top of your schedule, all right? And remember that on the day of the exam, you will have to sign off on that academic honesty policy before the exam will open for you. Once the exam opens, you will have a time limit. And although the exam, all the answers are in Canvas, there are some questions where you'll have to write down your calculations on a piece of paper and submit it, afterwards. And you'll have some time to submit it afterwards, okay? So that's the plan. Let me see if there are any questions. Seeing some questions here on the, let me open the chat here. So questions were about what the units are covered. Thank you, Alexa, for taking care of those. Yes, the exam is on the 20th. That's Monday, right? Yeah, Monday at 1 o'clock, all right? So I'll post out some more announcements. And Alexa, can you unmute and tell us what today's SI session is about?
Yeah, so today's SI session is just on what we learned today and what we were finishing up from last packet or last unit. And on Monday, I'm planning to have an SI session before the exam.
Wow, that's awesome. Thank you. Appreciate that.
Go over like the entire exam portion of the this unit.
Perfect. Thank you so much. Appreciate that. Okay, guys, you heard it. So Alexa is your helper here, your coach. So please join her in her SI sessions. All right, we're gonna stop the meeting here. Let me stop the recording.